Imagine you're a cashier, and someone hands you a bill and asks for change using the fewest coins possible. With normal coins, you'd greedily grab the biggest one that fits, again and again, and you'd be right. But today the coin sizes are strange, and that greedy instinct quietly gives the wrong answer. To find the true best, you have to explore choices, and that exploration is where our whole story begins. Let's make it concrete. Our coins are worth 1, 3, and 4, and we want to make 6. Greedy grabs a 4, then needs 2 1s for 3 coins total, but 2 3s make 6 with just 2 coins, so Greedy loses. The lesson is that we cannot trust a single rule of thumb. We have to actually consider our options. So how do we consider every option without missing anything? We ask a simple recursive question. To make an amount, we try each coin as our first pick, then we ask for the fewest coins to make whatever remains. The best overall answer is 1 plus the smallest of those smaller answers. This is a beautiful idea because the big problem is built out of smaller copies of itself. Making 6 depends on making 5, 3, and 2, and making 3 depends on making 2, 0, and, well, a negative we throw away. Each answer leans on answers to smaller versions of the exact same question. Let's let this recursion run all the way down and watch the tree it grows. Every node spawns up to 3 children, and those spawn 3 more, and the branching keeps multiplying. What started as one honest question fans out into a sprawling thicket of sub-questions. Now look closely, and something wasteful jumps out. The amount 2 appears here, and over here again. Each time we solve it from scratch as if we'd never seen it before. We are re-answering identical questions over and over, and the tree is full of these twins. How bad does this repetition get? As the target grows, the number of nodes in this tree explodes exponentially, roughly tripling with each step deeper. A target in the mere dozens already means millions of redundant calls. This is the exponential wall that naive recursion slams into. But here's the insight that changes everything. The answer to fewest coins to make 2 is always the same no matter where in the tree we ask it. If we could just solve each distinct amount once and remember the answer, all those duplicate branches would collapse. The waste isn't in the question, it's in forgetting. This act of remembering has a name, memoization. We keep a notebook, and the first time we compute an amount, we write its answer down. Every later time we need it, we just read the notebook instead of recomputing. Solve once, reuse forever. Let's finish the row. Amount 4 can use the 4 coin directly, back to 0, so just 1 coin. Amount 5 is best as 4 plus 1, giving 2. And amount 6, our goal, is best as 3 plus 3, also 2 coins. The table is complete. Step back and admire what we did. We answered a question that a naive tree would have needed exponential effort for, using a short walk across a handful of cells. The explosion is gone, replaced by a calm, orderly sweep. This orderly sweep, filling a table so each answer builds on smaller ones, is dynamic programming. But knowing it takes 2 coins isn't quite satisfying. Which coins? A good answer should be able to point at the actual solution, not just its size. Happily, the table already holds that story, we just have to read it backwards. Backtracking works like following a trail of breadcrumbs. Stand on cell 6. We remember its winning move was the coin 3, which brought us here from cell 3. So we pocket a 3 coin and step back to cell 3. Now we're on cell 3, and its winning move was also the coin 3, stepping back to cell 0. We pocket another 3, and cell 0 is our base, the trail ends. We started with nothing and reconstructed the exact answer, 3 plus 3. The trick that made backtracking painless was a small note in each cell. Alongside the count, we quietly recorded which coin won. That single breadcrumb per cell turns how many into which ones, at almost no extra cost. Remember the decision, not just the value. We've conquered a one-dimensional problem, a single row of amounts. But the real power of dynamic programming shows when the problem lives on a grid. To see that, let's meet a completely different puzzle. One about comparing sequences. Here are 2 words, and we want their longest common subsequence. A subsequence keeps letters in order but lets you skip any you like, no rearranging. The longest common subsequence is the longest string of letters that appears, in order, inside both words. It measures how much two sequences secretly share. This matters far beyond word games. It's how diff tools find what changed between two versions of a file, and how biologists align strands of DNA to spot shared ancestry. Underneath, it's the same question: how do two sequences line up? And it hides the same exponential trap. Let's build the recursive intuition again by looking at the last letters of each word. If those two final letters match, they can both join the shared subsequence, and we recurse on the two words with their last letters chopped off. That match is a guaranteed win we happily take. But if the last letters differ, we can't use both, so we face a choice. Either drop the last letter of the first word and ask again, or drop the last letter of the second word and ask again. Whichever choice yields the longer common subsequence wins. Match rewards us, mismatch forces a branching decision. You can feel the recursion tree looming again. Every mismatch doubles our work, one branch for each word we might shorten. Left alone, this is another exponential explosion, and once again it's riddled with repeated subproblems, the same pairs of prefixes asked over and over. So we reach for the same cure, a table. But now each subproblem is defined by two things: how much of the first word and how much of the second we're considering. Two dimensions of state naturally become a two-dimensional grid, one axis per word. Each cell will hold one number, the length of the longest common subsequence of the prefix ending at that column and the prefix ending at that row. The bottom right corner, using both words fully, is the answer we ultimately want. Every other cell is a stepping stone toward it. We need a foundation to build on, and it comes from empty prefixes. If either word contributes nothing, the longest common subsequence is trivially zero, so the entire top row and the entire left column are filled with zeros before we begin. That border is our launch pad. Now the fill rule, and it comes straight from our two cases. If the letter of this column matches the letter of this row, the cell equals the diagonal cell up and to the left plus 1. A match extends the shared subsequence sitting in that diagonal neighbor. If the letters don't match, we can't add anything, so we inherit the best we already had. The cell takes the larger of its top neighbor and its left neighbor. Those two neighbors represent dropping one letter from one word or the other, exactly the branching choice from before, now just a glance away. Let's start filling, row by row, left to right. The first interior cell compares the first letters of each word. Match or mismatch, we apply the rule, look at the already known neighbors, and drop in a value. Notice every neighbor we ever need has already been computed. As we sweep across the first row, we mostly copy values sideways, since long stretches won't match. Each cell quietly asks its question, checks its neighbors, and settles on a number. It feels almost mechanical, and that's the point. Hard thinking has become simple bookkeeping. Row by row the grid comes alive. Watch how a single match lights up a diagonal move and nudges the count higher, while mismatches keep pulling the best from above or the left. The numbers gently climb as we move toward the bottom right, each one earned from cells already in place. And there it is. The bottom right cell holds the length of the longest common subsequence of the two full words. One number, the payoff of the entire grid. But just like with the coins, a length alone leaves us curious. Which letters actually make up that shared subsequence? Once more we backtrack, tracing our steps from the corner. The rule mirrors how we filled. When we stand on a cell that came from a diagonal match, that letter belongs to our answer, so we record it and step diagonally up and to the left. When instead the cell just inherited from a neighbor, no letter was added there, so we simply follow the arrow back toward whichever neighbor gave the value, up or left. We keep walking this trail of arrows, collecting a letter on every diagonal step, until we reach the zero border. Reading the collected letters in order gives us the actual longest common subsequence, not just its length but its very identity. The same grid that measured the overlap also remembered how to reconstruct it. Fill forward to find the answer, walk backward to recover it. Notice the deep pattern uniting our two puzzles. In both, a giant problem broke into overlapping smaller copies of itself. In both, naive recursion exploded exponentially by resolving those copies, and in both, a table storing each subproblem once tamed the explosion completely. That is the entire secret of dynamic programming, distilled into two conditions. The problem must have optimal substructure, meaning its best answer is built from best answers to smaller pieces, and it must have overlapping subproblems, the same small pieces recurring again and again. When both hold, a table is your weapon. And there's a reliable recipe hiding in everything we did. Define what each cell means. Pin down the base cases. Write the rule that builds a cell from smaller ones. Fill in an order that respects dependencies, and keep a breadcrumb per cell so you can backtrack to the real solution. So the next time a problem feels like it wants you to try everything, and you sense the same questions echoing inside that search, don't panic at the exponential tree. Give each distinct question a cell, fill the table once, and let remembered answers do the work. That shift, from re-deriving to remembering, is dynamic programming, and now it's yours. If this made it click, subscribe for more visual math.